morning, everybody. Raise your hand if you brought leftovers for lunch today. Nobody? There's a few. Very good. Excellent. Hope everyone enjoyed their holiday. Welcome back. And let's get to it. Dr. David Apps is going to present today, originally hailing from the great state of Minnesota. Minnesota, right? Yeah. Good, got it. After going to medical school at Northwestern and graduating in 2010, he finished his internship and came to CU and completed his residency in anesthesiology. He's currently an assistant professor doing his clinical work at Denver Health, and he's going to speak to us today about an area that probably doesn't get enough attention from us. I think especially in today's world, if you've had a chance to look at some of the news this past weekend and some of the reports that came out about our environment. David's going to talk to us today about the environmental impacts and considerations of anesthesia. So appreciate you coming. He's also going to give this talk at Crash this coming February.
All right, thank you. All right, good morning, everybody. Thank you for having me. Hope everybody had a nice Thanksgiving. It's nice to see a lot of friendly faces in the audience today, but for those who don't know me, I'm David House, like you said. I'm at Denver Health. And welcome to my Grand Rounds lecture, Volatile Anesthetic, and their environmental impacts and considerations. So the goals of this talk are to first gain an understanding of the environmental impact of aspects of our anesthesia practice. We'll gain an in-depth appreciation of sevoflurane specifically and its potential advantages and disadvantages. We'll examine how cost plays a role in all of this, and we'll take a look at some future directions in the field of anesthesiology and healthcare at large with respect to the environment. So, as we all know, global climate change has played a prominent role in recent news cycles, and I don't think it'll be any underestimation that it'll most likely only continue to grow in profile and importance in the future. In October of this year, there was a report published by a multinational organization that was covered in the New York Times with this headline and on Fox News with this headline. It was put out by the Intergovernmental Panel on Climate Change, which is a group of UN-commissioned scientists that advise world leaders on global climate change-related topics. And essentially, the main findings of the report were that the climate change catastrophes that many scientists had predicted would happen with a 2.5 degrees Celsius rise from pre-industrial temperatures were now actually expected to happen with only a 1.5 degree increase from those same temperatures. And that we were on pace to have this happen by the year 2040, which is actually several decades sooner than they had originally predicted. And so the bottom line of this report was to prevent this, global greenhouse gas emissions need to be reduced by 45% from their 2000 levels by 2030, 12 years from now. So I'll give you the bottom line of this talk right up front. All of the volatiles that we use are potent greenhouse gases. On this page, there's two numbers that probably should stand out to you. First, the carbon dioxide is set to a global warming potential of 1, and desflurane is 2,540 times more potent. So how did we get here? Well, in 1985, scientists discovered a hole in the ozone layer, and that led to the Montreal Protocol in 1987, which was a commitment by nations to reduce ozone-depleting gases, specifically the CFCs. 10 years after that, in 1997, there was the Kyoto Protocol, which was a commitment for countries to reduce their greenhouse gases. Throughout all of this, volatile anesthetics and nitrous oxide were deemed medically necessary, and as such, to date, there's no regulation regarding their use or disposal. Now, there's OSHA standards for occupational exposure, but once they're scavenged from the operating room, they're vented unchanged directly into the atmosphere once they leave the hospital. Here's some definitions that we'll just go through as we go forward. ODP will stand for ozone depleting potential, GWP for global warming potential, and then a GWP with a time subscript is the global warming potential relative to carbon dioxide over a specified time horizon. So prior to 1999, there hadn't been much work done on volatile anesthetics and their environmental impacts. There was a little bit of work done to determine their atmospheric lifetime, which had been the basis for kind of a rough idea of their ozone depleting potential and global warming potential. But in 1999, this group from Germany published in BJA an experimental model of gas degradation due to hydroxyl radical and photolysis, which they estimated would occur in the upper atmosphere. And this is the first time that ODP and GWP were actually calculated for volatile anesthetics. For the following 10 years, not much was done on this topic until 2010, when Sulbeck Anderson and his group from the Jet Propulsion Laboratory at Caltech University published this article in BJA in 2010 that experimentally measured the infrared spectra of our volatiles and further refined the calculated global warming potentials for our common gases. They calculated the halogenated anesthetic contribution to radiative forcing of climate change, and I'll pause here for a second to give us a couple of definitions. We'll see something called the atmospheric window, which is the spectra of infrared radiation leaving Earth's atmosphere or Earth's surface out into outer space. And then there's radiative forcing, which is the absorption spectra of a gas in Earth's atmospheric window. Or to say another way, it's the imbalance between infrared radiation entering and leaving Earth's atmosphere. And so radiative forcing is dependent on the wavelength of different gases' absorption features. And this study was the one that set the stage for further atmospheric studies to follow. So this graph was kind of the meat of the study, and I'll just highlight a couple things. Number one, the x-axis is the infrared spectrum with its wave numbers. And you can see the atmospheric window highlighted there, and then superimposed on that are the absorption spectra for isoflurane, sevoflurane, and CFC11. And as you can see, the majority of their absorption occurs within this so-called atmospheric window. In 2011, Ishizawa from MGH published this article in ANA, which is the first to really escalate concern for the ecotoxicological consequences of our common anesthetic gases. And for those of you who might be familiar with this paper, although he was erroneous on the subject of halogenated anesthetics that he claimed were all ozone depleting, he did bring important attention to the dual ozone depleting and global warming potential of nitrous. And he also importantly brought attention to the scale at which nitrous is used across the country and the world, which was 20 tons at MGH alone in the year 2006, and 35,000 tons nationally across the U.S. healthcare sector. In 2012, Sulbeck Anderson and his group at the Jet Propulsion Laboratory at Caltech published this paper in response to the 2011 Ishizawa article, which has given us our most up-to-date science on the GWP radiative forcing and ODP of our volatile anesthetics, including nitrous. And he reintroduced the graph of the absorption spectra of volatile anesthetics in the context of the atmospheric window. Here you can see that similar graph to what we saw earlier, and now we have ISO, SIVO, and DES superimposed onto that graph in these light gray absorption spectra. This is the table of data that comes from that paper. There's a lot on here, so we'll spend just a quick minute going over it. We can see the global warming potential for all of our gases for 20 and 100 time-year horizons, the ozone depleting potential of our gases. Specifically, if we look at the global warming potential over a 100-year time horizon, we can see that desflurane is by far the highest, and sevoflurane by far the lowest. Nitrous and ISO are both ozone depleting, and if there's any kernel of good news, it's that DES and SIVO are not ozone depleting potential gases. They also gave us atmospheric lifetimes for these gases, starting with sevoflurane at 1 year, ISO at 3, DES at 14, and nitrous at 114 years. In 2012, this study was published in ANA to examine the life cycle climate change impacts of 5 anesthetic drugs: ISO, DES, SIVO, nitrous, and propofol. They used a cradle-to-grave approach examining resource extraction, drug manufacturing, transport to healthcare facilities, drug delivery to the patient, and disposal or emission to the environment. And at each stage, the material inputs and emissions were considered. Here you can see the greenhouse gas emissions for the manufacturing of desflurane, ISO, and SIVO. And you can also appreciate that for desflurane there are also greenhouse gas emissions associated with the energy required to deliver the gas, which is the vaporizer has to be constantly maintained at 39 degrees Celsius, compared to the others that can just be delivered at room temperature. The emissions were calculated in CO2 equivalents, and fresh gas flows were assumed to be 1 liter per minute for DES and ISO and 2 liters per minute for SIVO. Here you can see the greenhouse gas emissions when they include the agent release into the atmosphere after it's been used. And the light pink portion are the emissions associated with the agent release for desflurane, ISO, and SIVO. So what we can take away is that the life cycle greenhouse gas emissions for DES are 15 times greater than that of ISO and 20 times greater than that of SIVO. ISO and SIVO have similar emission profiles in an oxygen and air mixture, which is largely due to the higher fresh gas flow rates in this analysis for SIVO. And when co-administered with nitrous oxide, emissions for ISO increased by 65%, and those for SIVO increased by 900%. In 2015, this study was published examining the atmospheric content of the halogenated volatile anesthetics. This is the first study to estimate global warming contribution from each agent using a top-down analysis, meaning that instead of making these calculations in laboratories and extrapolating them to the globe, they actually measured atmospheric samples from 4 different locations across the planet, ranging from the North Pacific to the Antarctic and 2 locations in Europe. They measured halothane, ISO, DES, and SIVO. The top is halothane, and no surprise, that's been decreasing in the atmosphere over the 14 years of this study from 2000 to 2014. And then specifically what I want you to pay attention to is that desflurane has the fastest rate of increase of the 3 volatile anesthetics that we commonly use. They look at their emission profile, and the emissions in terms of gross weight are listed in this figure. The lined portion is desflurane, and the white portion is SIVO. And then when you translate that into carbon dioxide equivalents, the line portion down here is desflurane, and the white portion is sevoflurane. So the conclusions of this study were that collectively volatile anesthetics can have an appreciable impact on radiative forcing, and in the year 2014, by this measurement, approximately 3.1 million tons of CO2 equivalents were released into the atmosphere, of which approximately 80% was due to desflurane. So these are kind of abstract things that we've been going over. I really like this table because it provides a concrete analogy that I think we can all understand, which is what's the equivalent of, say, driving a vehicle. This compares our volatile anesthetic use to driving a car that gets 24 miles to the gallon. And so we can see that if we're using sevoflurane at 2 liters per minute for an hour at 1 Mach, that's equivalent to driving 8 miles. If we're using ISO at 1 Mach for 1 hour at 1 liter, that's 7 miles. If we're using desflurane at 1 liter for an hour, almost 200 miles. And if we use DES at 2 liters per minute, nearly 400 miles driven. So how significant are greenhouse gas emissions in the context of the healthcare sector, and how significant is the healthcare sector in terms of total national emissions? In 2009, this study in JAMA looked to examine that question. They used 2,000 U.S. healthcare sector data, and they found that the U.S. healthcare sector accounted for 16% of the GDP and 8% of the nation's greenhouse gas emissions, which for comparison in 2004, the National Health Service in Great Britain accounted for 3% of the total carbon dioxide emissions. In 2013, the U.S. healthcare sector was now responsible for 10% of U.S. greenhouse gas emissions, and these authors estimated that this was responsible for over 400,000 disability life years lost, which is comparable in its scope to that of preventable in-hospital deaths. Here you can see that graphically represented. The orange bars are the absolute emissions from the U.S. healthcare system, and the blue line is the percentage of the nation's U.S. greenhouse gas emissions of the United States, both of which are rising over time. So let's tie this all together for us in the operating room and see what kind of impact we have. This study was published in 2017 in The Lancet, and it examined the carbon footprint of the operating room system for 3 different hospitals in 3 different healthcare systems for the year 2011. They looked at Vancouver General Hospital in Vancouver, the University of Minnesota in Minneapolis, and Oxford, the John Radcliffe Hospital in Oxford, England. They looked at 3 different scopes. First were the emissions associated with volatile anesthetics. Second were the emissions attributable to the energy consumption of the operating rooms. And third were the emissions attributable to the supply chain and waste. So the important things to note were that for the volatile anesthetics, Vancouver General and the University of Minnesota relied primarily on desflurane for their volatile anesthesia, and John Radcliffe Hospital in England didn't use any. They only used sevoflurane and iso. So that translated to just under 2 million kilos of carbon dioxide equivalents generated from desflurane alone at Vancouver and Minnesota. And for total volatile anesthetic CO2 equivalents for that year, just over 2 million kilos for the North American hospitals, and only 200,000, 1/10 as much for John Radcliffe Hospital in England. If we look at the energy consumed from the different operating room systems, we can see that there is a significant difference across the 3 different hospitals. This is largely due to the composition of their respective energy grids. In Vancouver, they get most of their electricity from hydroelectric power, and in England, it's primarily all coal-burning power plants. These are the emissions due to their surgical consumables and waste streams, and here you can see really there's not a whole lot of difference amongst the 3 different hospitals. So putting them all together, we can see that there are significant differences in the emissions associated with their electrical consumption and with their volatile anesthetics. If we look at this in a graphical representation, you can see that for Vancouver, their volatile anesthesia accounted for over 60% of the carbon footprint of their operating room system. At the University of Minnesota, that was over 50%, and at John Radcliffe Hospital in England, less than 5% was due to their volatile anesthetics. So, 2 highlights. Number 1, it's important in terms of the emission profile of an operating room system to know what the energy grid consumption is, but more importantly and modifiably, for the North American hospitals, volatile anesthetics were the largest contributors to their greenhouse gas emissions by far. They were 10 times greater than that of John Radcliffe Hospital in England, and this is actually notably with one-third fewer cases performed. They did approximately 20,000 cases at the North American hospitals in comparison to 30,000 cases done at John Radcliffe. And the disparity in their carbon footprint can be accounted for largely by the preferential use of desflurane at the North American sites. So, to circle back, volatile anesthetics all have different lifespans that range from 1 year for SIVO, 14 years for DES, and 114 years for nitrous oxide. And they all have different global warming potentials that range from 130 for sevoflurane all the way up to 2,540 for desflurane. So now let's take a closer look at sevoflurane specifically. We'll look at the advantages it has, we'll look at any disadvantages it has, maybe cost plays a role. So in terms of the advantages, we've already covered that it has the smallest environmental burden defined by GWP and atmospheric lifetime. And there's also instances of clinical advantage, mask inductions, pulmonary disease, etc. Disadvantages, well, we've all learned that you need to run it at 2 liters minimum flow, and this is because of compound A-induced nephrotoxicity. So let's see where that came from. Sevoflurane was approved for use by the FDA in 1995, and I'm just going to read from you directly from the product insert, which is also the same as the FDA website, just so we all know exactly where this recommendation comes from. This is from the warning section, which says, although data from controlled clinical studies at low flow rates are limited, findings taken from patient and animal studies suggest that there is a potential for renal injury which is presumed due to compound A. Animal and human studies demonstrate that sevoflurane administered for more than 2 MAC hours at fresh gas flow rates of less than 2 liters per minute may be associated with proteinuria and glycosuria. Here's the evidence for that. Sevoflurane may be associated with glycosuria and proteinuria when used for long procedures at low flow rates. The safety of low-flow SEVO on renal function was evaluated in patients with normal preoperative renal function. One study compared SEVO to an active control administered for greater than 2 hours at fresh gas flow rates of less than 1 liter per minute. Per the study criteria, one patient in the sevoflurane group developed elevations in creatinine in addition to glycosuria and proteinuria. This patient received sevoflurane at fresh gas flow rates of less than 800 milliliters per minute. And this is compared to the control group where no one had any elevations in serum creatinine. So after this, researchers started to study the human effects of low-flow sevoflurane and compound A. In 1995, this study looked at flow rates on compound A production of sevoflurane anesthetics with soda-lime CO2 absorbers. It was published in the BJA. They randomized 24 ASA 1 and 2 patients undergoing tympanoplasty to sevoflurane anesthetics at different flow rates, 1, 3, and 6 liter per minute, and they measured the compound A in the circuit at different time points. No surprises, the 1 liter per minute group had the highest concentrations of compound A, although it's important to note that these concentrations were actually very low, less than 20 parts per million. In 1997, this study was published in Anesthesiology, and this looked at the effects of low-flow sevoflurane anesthesia specifically on renal function. They randomized 48 ASA 1 and 2 patients undergoing gastrectomy for gastric cancer to either low-flow sevoflurane at 1 liter per minute, high-flow sevoflurane at 6 to 10 liters per minute, or low-flow ISO at 1 liter per minute. They used beryllium CO2 absorbent, which we'll all remember is basically potassium hydroxide, and it's actually the most compound A forming CO2 absorbent for the low flow groups, and they use glass balls instead of any CO2 absorbent for the high flow sevoflurane group, and this was for their control group that would have 0 compound A exposure. They obtained blood samples preoperatively and on post-op days 1 through 3 to measure BUN and creatinine, and they collected 24-hour urine samples preoperatively and post-op days 1 through 3 to measure creatinine, and then these 2 kidney-specific enzymes, NAG and AAP. The results were this graph up here for the low-flow sevoflurane group. Interestingly, compound A peaks at about 2 hours, and then after that slowly decreases in the system. They found that the average concentration of compound A in the low-flow sevo group was about 20 parts per million, which trended down over time. The average case duration was about 6 hours, and the results were that no differences existed amongst groups post-operatively. BUN decreased across all groups. Creatinine decreased on post-operative day 3 in the sevoflurane groups, high and low flow, but not in the ISO group. Creatinine clearance increased in all groups, and 24-hour urinary excretion of NAG and AAP increased across all groups. So there are no differences whether they were exposed to compound A or not, and no differences whether they were exposed to sevoflurane or isoflurane. In the year 2000, in ANA, they looked at the study again, but they extended the time frame over which patients were exposed to compound A. They randomized 30 ASA 1 and 2 patients with head and neck cancer scheduled to undergo surgery for over 10 hours. Patients were randomized to the same groups, low flow and high flow sevoflurane and low flow ISO. Again, they used beryllium carbon dioxide absorbent for the low flow groups and glass balls for the high flow sevo group. They measured compound A. They measured blood samples preoperatively and on post-op days 1 through 3 to measure their BUN and creatinine levels. They collected 24-hour urine samples, just like they did before, pre-op and post-op days 1 through 3, to measure creatinine, NAG, albumin, protein, and glucose. Average case duration was 18 hours. The plot of compound A in the upper right-hand corner, you can see again a peak at about 2 hours, after which significant downtrending over the remaining time frame of the surgeries. And the average area under the curve for compound A in the low-flow SIVO group was 277 parts per million hours. For reference, renal injury was surmised to occur at a range of 150 to 342 parts per million hours based on rat studies that had been done. And the results of this study, like the previous one, were that there were no increases in creatinine, no decreases in creatinine clearance, no differences amongst any of the groups. There were increases in urinary excretion of protein, albumin, glucose, NAG across all groups, and there were no differences. So these studies were actually done with old legacy CO2 absorbents that aren't used very much anymore, if at all. So in 2007, this study looked at 7 modern CO2 absorbents that were tested in a patient model under low-flow sevoflurane conditions for 3 hours. Now, I'm not sure what kind of CO2 absorber all the different hospitals use, but at Denver Health, we actually use Draeger machines, and this Draeger-Zorb 800 CO2 absorber, which I've highlighted up here at the top. The important thing to point out here is that 82% of it, the vast majority, is made up of calcium hydroxide, which is non-compound A forming, and only 0.003% is potassium hydroxide, and only 2% is sodium hydroxide, the traditional strong base compound A forming CO2 absorbers. The results of their study were that conveniently the Draeger-Zorb CO2 absorber had the most compound A formation. They used different units here, so it was 1695 parts per million minutes, but to convert that, that's actually only 28 part per million hour, which is much, much less than we saw in the previous study. And then in 2008, they looked at low-flow sevoflurane using these modern absorbers in human patients. They measured compound A through the case, and really no surprises in their findings. Compound A measurements continue to be very low, downtrending over time. And the thing that I thought was actually the most important about this study was from their results section. They wrote that although transient nephrotoxicity was demonstrated with previous studies, respectively with these values for their compound A exposure in humans, the majority of publications demonstrate no nephrotoxicity in humans with the use of sevoflurane in combination with any kind of absorbent. The results of this study, together with the results of the previous lab study, confirm these observations, and from these results, they therefore conclude that SIVO can be safely used in low-flow anesthesia in contradiction with the FDA recommendation to use a fresh gas flow of more than 2 liters per minute. There's also one more thing. This editorial, published actually back in 1997 in Anesthesiology, brought one thing to light which sort of like scratches my personal itch about trying to find the tie to dark corporate money and all of this, which is that the research done in animal models on compound A and nephrotoxicity was done by the same person who conducted the only trial that the FDA cited in their warning for sevoflurane, who's also the same person that lobbied the FDA for that warning to be put in place, who was also on the development team of desflurane, who was also paid by, at the time, Omeda, who's now Baxter. So I think that's a little bit of context for all of this. So there's an overwhelming body of evidence that supports the safe use of sevoflurane in low-flow anesthesia. And even in the presence of strong bases like Barolime or Sodalime, compound A-mediated nephrotoxicity has never been demonstrated in people. Studies that have demonstrated compound A-mediated nephrotoxicity have not had their results repeated. And newer CO2 absorbents contain only small fractions of strong bases, which leads to minimal compound A production at low flows. So a strong argument can be made that the 2 liter per minute fresh gas flow FDA recommendations is itself not evidence-based. So how about cost? Sevoflurane is expensive, isn't it? So maybe we can rationalize that desflurane may be environmentally bad, but can we save money by using ultra-low flow anesthesia? And we'll see if there's any cost savings that might be hidden in all of this. So in 1992, Dion published an equation in the CJA for calculating the cost of volatile anesthetics. The following year, Lokenshire published an equation for calculating cost per MAC hour and a method for establishing cost equivalence between different volatile anesthetics. So here's that equation. Variables are essentially the cost of the volatile flow, the MAC of it, molar weight, density, temperature, etc. So we can do a thought experiment, which is assuming that everyone still uses 2 liters per minute fresh gas flow for SIVO. Could there be a cost savings for using low flow desflurane? And if so, where exactly is the break-even point for the 2 gases? So you can set the MAC hour costs for DES and SIVO equal to each other, which is this equation across the top. We can plug these in for our variables, and we can see that at Denver Health, we spend about 28 cents per ml for our sevoflurane, 63 cents per ml for our DES, which means that for cost equivalence, we need to run our DES at 0.36 liters per minute. At the university, that would be about 0.43 liters per minute. At the VA, about 0.47 liters per minute. And at Children's, about 0.38 liters per minute. So at Denver Health, our annual volatile anesthetic budget is approximately $300,000. From January through September of 2017, we spent just over $236,000 on our volatile anesthetics. In January through September of 2018, we spent only $110,000. This represents a 53% savings in 2018 over 2017 and 51% under our annual projected budget. The only intervention was around the first of the year. The majority of providers switched to sevoflurane as their default volatile anesthetic, if you will, with about a 2 liter per minute fresh gas flow as their practice habit. This study in 2016 in ANA examined the cost efficacy of switching from a legacy CO2 absorber, soda lime, to a non-reactive carbon dioxide CO2 absorber, litho lime, and reducing fresh gas flow rates, and to examine whether or not there was any cost savings associated with it. All of the providers in their department were instructed to reduce their fresh gas flows using SIVO to 1.25 liters per minute or less. And the hypothesis they looked at was that the cost savings from reduced SIVO consumption would modestly exceed the incremental cost of their premium CO2 absorbers. And what they found was that the savings on SIVO administration ended up cost neutral with the extra cost of their litho-lime absorbent. And they attributed this largely to practice inertia. Most providers didn't actually reduce their flows to the goal. And there was some imprecision in their sevoflurane ordering, lag time, extra storage, etc. But it did prove to be at least cost neutral. And what came from this is they came up with a nomogram and a set of questions that a department can use to analyze whether or not there is any predicted cost savings with switching to a non-compound A forming CO2 absorber. So while multiple factors determine overall cost, it's likely that for many institutions, transitioning away from preferential desflurane use represents significant cost savings. And if so interested, it can be fairly simple to calculate cost savings or cost neutrality should an institution decide to optimize its operating room carbon footprint. So at this point, we can address the counter-argument, which is, okay, this might be bad, but really it's just a drop in the bucket compared to the carbon dioxide release and fossil fuel burning across the planet, and that the primary thing to consider is patient safety, or simply I'll just practice how I want to. And I think that a lot of these counter-arguments are summarized quite nicely in this editorial from ANA in 2013, which I'll quote from, which is, the overall contribution of inhalational anesthetics to greenhouse gas emissions is minuscule, approximately 0.1% of that of the CO2 released by global fossil fuel consumption. And so I've seen the 0.1% figure, and maybe you have too, cited a few times, But if we look at where that actually comes from, it comes from that 2012 Silbeck-Anderson et al. Article that we looked at earlier, which actually just looked at the University of Michigan alone and extrapolated their emissions to global anesthetic emissions. And the important things to note were that the University of Michigan did over 40,000 cases in the year they looked at and used only 6 liters of desflurane. So they use hardly any desflurane at all. And this number also doesn't account for nitrous oxide or any life cycle assessments of the volatile anesthetics. So in reality, the 0.1% is probably the most idealized number that we could hope for, and not what it actually is. They also go on to say that we believe the notion that the minuscule impact on the environment compares to clinical issues such as cardioprotection, airway irritability, rapidity of recovery, and cost is inappropriate. Well, I think that we've addressed at least a few of these things already, and the other notable thing from this editorial is under the conflicts of interest section. I know this is small print, but the word Baxter probably jumps out at you a few times if you look closely. So where are we going from here? We'll touch on nitrous oxide destruction, waste anesthetic gas reclamation, the potential for novel volatile anesthetics, and common sense, and probably most importantly, common sense strategies for our personal practice. So nitrous oxide actually has the ability to be catalytically destroyed and split into nitrogen and oxygen. There's a commercial system that exists for this. It's made in Japan called Anesclean. This study looked at this system, which was employed on the labor and delivery ward at Karolinska University Hospital in Stockholm, Sweden. And they found that 95% of their collected nitrous was able to be catalytically destroyed. And then they did a life cycle assessment that looked at everything from the manufacturing of the equipment to shipping it from Japan to Sweden, etc. That did show an overall greenhouse gas benefit to the system. There's waste anesthetic gas reclamation. There's a company in Canada that produces a system to capture volatile anesthetics at either the level of the machine or the central HVAC system, which allows for desorption of halogenated agents as liquids, which allows for their potential processing and reuse. Now, although this is in place in some Canadian hospitals, this isn't yet FDA approved, and there still needs more research on the topic of reclamation, reuse, and reprocessing of volatile anesthetics. In terms of novel volatile anesthetics, we've all probably heard about xenon. It's a noble gas with profound analgesia, neuroprotection, hemodynamic stability, low blood gas partition coefficient, all great things, and even better, no known detrimental ecotoxicological effects. At the time, though, it's limited by high cost and the energy consumption of fractional distillation or liquid air required to make it. So its use would only be possible in a closed circuit system with the reclamation of the gas, which we can't do at this time. So probably the most applicable and easiest to do is managing our fresh gas flows. So if you're using sevoflurane for maintenance of anesthesia, aim for 1 liter per minute fresh gas flow. If you're using ISO or DES, aim for a closed circuit maintenance of anesthesia. You can do that by calculating your patient's oxygen consumption, which you can estimate to be usually about 5 milliliters of oxygen per kilo per minute. And then you can calculate your minimum necessary fresh gas flow, which is the patient's oxygen consumption plus any leaks in the system. And then another thing that I personally like to do is during intubation, assuming you've done a standard induction and you've been masking the patient with some volatile, when you take the mask off and go to intubate, instead of turning your vaporizer off and leaving your fresh gas flows on, leave your vaporizer on and turn your fresh gas flows to 0. That way any volatile that's in the circuit will remain in the circuit and won't be discharged into the operating room. And that way, once your airway is secure, you reconnect your circuit. All you do is turn your fresh gas flows back up, and all of your volatile anesthetic is just delivered to the patient immediately. So kind of as we wind down, according to the U.S. Energy Information Administration, the healthcare sector is the second largest energy consumer in the United States. The inpatient the inpatient facility, and notably perioperative care, consume the most of the healthcare sector. As physicians, we've been called to a life of stewardship, and as anesthesiologists, we have the ability to expand our advances in patient safety and individual outcomes to include the world we live in, and we're uniquely positioned for leadership in the area of sustainability. The topics we've covered today have covered the value of greening our operating rooms, and we've seen that the operating room is an area for significant impact and savings. And by implementing these strategies, we have the ultimate goal of affecting the triple bottom line of patient safety, community health, and cost reduction. So to summarize, the take-home points are there are differences amongst our anesthetics regarding their environmental impact, with sevoflurane being by far the best and desflurane by far the worst. The safety concerns that we've all learned about sevoflurane are not supported by research, and there are significant cost savings that are likely with reduction in desflurane use. And anesthesia is uniquely positioned to impact health from a patient to a global level through our individual decision-making. Special thanks to these people who helped with some information for this talk, resources, and thank you. I have time for questions. Tony.
So Dave, with respect to the FDA warning, would you suspect that if somebody were to have some renal insult because of the use of sevoflurane, that they could have a basis for allowing you to go
That's always everyone's rationale for continuing to deliver SIVO at 2 liters per minute. I'm not a lawyer, so I don't know. But I will say that sevoflurane has been in use for over 20 years, and to my knowledge, there has never been any clinical instance of perioperative renal failure or renal dysfunction that has been pinned on sevoflurane, nor is there any lawsuit that has ever implicated sevoflurane. And this actually, to my knowledge, hasn't been readdressed with the FDA since 1996. That's a fair point. The point of yes. So I think that you're referring to the recommendation I had about the induction period of anesthesia. Whether you leave it on or off, that's actually not the important thing. The important thing was there's ability to save on just wasted gas in terms of money and in terms of just occupational environmental exposure by turning the fresh gas flows off during the period of time where the circuit is disconnected and would just otherwise be blowing the volatile agent that was already in the circuit into the room. So whether you decide to leave the vaporizer on or off, that's a personal choice. It could go either way.
Great talk, David. What are the barriers to removing desflurane completely from your practice at Denver?
I think that there are certain instances where you could argue that it has a clinical advantage. Personally, at Denver Health, where I use it are in our trauma cases. Other people feel differently, but I use it in the trauma cases where there's a lot of hemodynamic instability and it's just rapidly titratable on and off. But for our regular elective cases, I pretty much never use it.
One of the graphs that you showed that looked at propofol relative to the environmental impact to the volatile anesthetics was a very small aspect of that propofol. What's the argument for just trying to use an IV anesthetic during that?
So there's a good argument for that. Just for the purpose of time, I I decided that propofol was a little bit outside the scope of this lecture. But in terms of its emissions profile, it's obviously minuscule relative to the others. There is the topic of wasted propofol and contamination to water and that aspect of it, but with respect to the emissions profile, yeah, it's not comparable. All right, thanks.